first type of buffer simply involves picking up a weak acid and its conjugate base. So we've taken HNO2 and then nitrite. We get it in the form of barium nitrate right off the shelf. First thing to do, set up your equilibrium expression that unites that conjugate pair. So we have HNO2 on the left and NO2 minus on the right. HNO2 being a weak acid dissociates into the conjugate base and H3O plus. We need to get the amounts of each of the components into our initial line. Notice that the barium nitrate moles, we have double that number of moles of nitrite itself because there are 2 moles of nitrite for every 1 mole of barium ion. From our initial line, we see we have a shift to products. X products are formed and minus X reactants are lost. So we have equilibrium amounts 0.52 minus X, 2 times 0.19 plus X, and X. And of course we can divide all of these by the volume that this buffer is contained in. Without knowing the volume, we'll just put VOL, volume total, and we'll see what comes of that. Now, HNO2 is a weak acid, so we will have a Ka expression to help us solve for X. Ka being the nitrite ion concentration multiplied by the H3O plus concentration divided by HNO2 concentration. We want pH here, so it's the H3O plus molarity that is of interest to us. We rearrange our equation to isolate for H3O plus molarity. That'll be equal to the Ka of this particular acid times the HNO2 molarity divided by the NO2 minus molarity. We can put some numbers in now. We'll leave Ka as it is, but we have 0.52 minus X moles of the acid and 0.38, that's 2 times 0.19, 0.38 plus X moles of the conjugate base. All divided by the volume. Same volume, so those will cancel. See, we don't need to know the total volume for now. And if X is much smaller than the 0.38, then we can neglect it. And we have simply Ka times the ratio of 0.52 over 0.38. This gives us an H3O plus molarity of 6 times 10 to the minus 4. And that gives us a pH of 3.2, so a rather acidic buffer this time.